This image shows the extreme precautions required when handling life-threatening pathogens. Moving infectious substances outside of controlled laboratory environments creates an immediate public health vulnerability. Yet, public health infrastructure relies on the massive volume of routine diagnostic samples, like standard blood work or viral swabs, that must be transported safely through the exact same public transit networks every single day. This diagram illustrates the globally standardized engineering solution to that logistical risk, the triple-layer packaging system. It relies on 3 strict physical barriers of containment. This system operates on a redundant architecture. If one layer fails, the next takes over. It is engineered to achieve zero leakage, zero cross-contamination, and zero human exposure during transit. These 3 layers are calibrated to safely carry 3 specific tiers of biological payloads: routine diagnostic specimens, high-risk Category A infectious substances, and Category B samples. By isolating the biological hazard within multiple fail-safes, this packaging transforms an active biological threat into a neutralized, stable unit, ready for the global transport grid. Looking at this diagram, we start at the system's outermost boundary, the outer packaging. This acts as the primary physical shield against the external environment. International regulations require this outer shell to be constructed of highly rigid material. Its exact purpose is to absorb extreme external physical impacts to protect the delicate containment layers nested inside. Physical strength alone is insufficient without precise communication. The exterior must feature clear regulatory markers, such as the internationally recognized UN 3373 diamond label, which categorizes the biological substance inside. The exterior must also display clear, uncompromised sender and receiver details. This ensures a strict chain of custody from the moment the box leaves the laboratory. If the internal payload contains any volume of liquid, the outer packaging must feature mandatory orientation arrows. These black, double upward arrows indicate exactly how the box must sit to prevent sustained pressure on the internal seals. Logistics personnel rely entirely on these external markers. The labels immediately dictate specific handling procedures, segregation rules, and emergency protocols for that exact package. The outer packaging acts equally as a communication device and a physical barrier. It translates invisible biological risks into universal logistical instructions. This exploded view reveals the internal architecture of containment. Passing through the rigid outer shell, we reach the next line of defense. This specific schematic shows the secondary packaging, often taking the form of a sealed, highly durable biohazard bag. Its core function is to act as an uncompromising, redundant, leak-proof barrier. This secondary layer completely seals in both the primary specimen containers and all required internal absorbent materials. Transporting multiple specimens inside a single secondary package is permitted under one strict regulatory rule. Each individual primary container must be separately wrapped. This individual wrapping prevents mechanical friction. If glass or hard plastic tubes rub against each other during turbulent transport, they can fracture. Isolation prevents both physical breakage and cross-contamination. The entire design of the secondary packaging assumes that the primary container might ultimately fail. It provides the definitive physical boundary separating a leaked hazard from the courier and the public. Penetrating the secondary bag brings us to the core component. Looking at this cross-section, we see the primary container. This vessel directly houses the biological specimen itself, whether that payload is human blood, cerebrospinal fluid, or a diagnostic swab. The baseline manufacturing requirements for this vessel are absolute. It must feature a securely sealed, leak-proof closure, typically a tightly threaded screw cap, and carry an accurate identification label. Surrounding this tube is a highly tested failsafe, the absorbent matrix. Logistics regulations dictate a precise capacity role here. The primary container must be surrounded by enough absorbent material to trap and hold the entire liquid contents of the specimen if a breach occurs. In a catastrophic fracture, this matrix rapidly neutralizes the liquid, locking the fluid into a solid state before it reaches the secondary barrier. Even without the secondary layers, this isolated view shows the engineered precision of the primary container itself. This exact design acts as the global standard baseline required for all UN 3373 Category B biological samples. The tight engineering tolerances of the seal are designed specifically to prevent aerosolization, the dangerous conversion of a liquid pathogen into a fine, inhalable mist during transit. True biological containment anticipates failure. It engineers a direct physical mechanism to instantly neutralize the payload exactly when the initial walls break. Pulling back from the physical materials, this packaging architecture is governed by strict international frameworks. These include the UN Model Regulations, the ADR, which dictates rules for road transport, and IATA, the strict regulatory body for air transport. The stringency of these regulations scales directly to the biological classification of the pathogen. This split-screen graphic compares the two main regulatory classes. Category A pathogens present a severe, life-threatening risk to humans or animals upon exposure. This includes viral cultures like Ebola or SARS-CoV-2. Because of the extreme risk, Category A transport is governed by the strictest UN compliance codes, UN 2814 for infectious substances affecting humans, and UN 2900 for animals. Category B pathogens represent a lower immediate risk. These are typically routine diagnostic samples collected for standard testing, like standard blood draws or urine cultures. Category B samples fall under the UN 3373 handling stringency, which allows for streamlined but highly secure logistical movement. The biological threat level directly determines the exact laws of physics the packaging must survive during certification testing. Before deployment, the triple-layer architecture undergoes rigorous physical stress testing. This dual-pane graphic illustrates the two core certification environments. Governed by IATA and ADR, the drop test measures blunt impact resistance. The fully assembled package must survive a free fall from 1.2 meters, simulating a drop from a courier's hands or a high-speed sorting belt, with absolutely zero internal compromise to the primary container. The pressure test is an extreme requirement mandated specifically for life-threatening Category A payloads. The primary and secondary containment layers must endure an internal pressure differential of 95 kilopascals, nearly equivalent to one full atmosphere of outward pressure pushing against the seal. This test ensures the vessels can withstand the rapid cabin pressure changes and altitude drops unique to cargo aircraft, preventing explosive depressurization. Subjected to a 95 kilopascal differential in a cargo hold, the plastic and seals experience intense physical strain, warping outward without ever fracturing. The triple-layer packaging system provides the invisible physical architecture required for modern medicine to function. It ensures that critical diagnostic science can cross borders without triggering localized outbreaks.